Okay, hello. Um, Quick show of hands. Who here is a programmer? Technical people. All right, cool. I'm going to talk about AI, and in particular, I chose this title for my talk because it has the word robust in it, and it has fast action games also in it. When I mean robust, what I mean is something that's predictable, something that is easy to understand, something that's easy to tweak, and something that is maintainable. And I'm gonna talk about our game and how we implemented AI in our action game. And a key word is the word fast here, because our game is especially chaotic, and it is something we have to deal with when we implement AI. First of all, let me see. About me, my name is Radu Cristea. I'm a tech director for Rikodu. We're a small team based in Cluj-Napoca. That's us over there at Gamescom. And I've been doing games for quite a while. I'm a game dev veteran, and having worked for Avalanche Studios, Gameloft, AI Game Dev. And at some point I turned indie, and that's how we started Rikodu. And I also had a soft spot for AI, especially. Let's talk about our project. And one thing, this is the second time I'm presenting this talk, and the first one being in 2016, when we started doing this project. And I'm gonna talk about how things changed and what went right, what went wrong, some assumptions that were accurate and some weren't. And this is an image from the beginning of our project. This is some concept art we started. Our game is a fast-paced action game. It's basically a twin-stick shooter in a world of machines. The player can build up a robot, and you will fight all these enemies. This is how it started. We started doing at a game jam, Ludum there, in April 2016. This is how it looked at the end of those 72 hours. It went well. People liked it, we liked it, and we decided that this is a cool idea and we could definitely turn it into a real game. This is how it used to look. And if I can play the video, this is our release trailer. And it's now on Steam in early access, and we're gonna do consoles and full release on Steam. If you guys can play the video. Pay attention to the enemy activity around. All right, so a lot of action. One thing to note is that it's multiplayer, both online and local, and you can have the game has to work for one player or 2 players, 3 players, and up to 4 players. And that's another thing we need to think about. So AI in video games, that's such a hazy and it has a very hazy and bad definition, and this is like my favorite definition of it, even though it's not actually defining it. So this guy, Matt Buckland, wrote a very good book on game AI. And he says that to be enjoyable, an AI must put up a good fight, but lose more often than win. It must make the player feel clever, sly, cunning, and powerful. It must make the player jump from his seat, shouting, "Take that, you little shit." I like this definition. So, on AI in Frankie's Revenge, these are the challenges we need to tackle. So, we need to create some kind of dramatic pacing. We need to make the enemies challenging. It needs to complement the level design, because we have a lot of levels, and the levels have different mechanics. It should handle the enemy decision making. It should handle enemy positioning. So that means, where do enemies position themselves around you? Difficulty scaling, this is especially complicated, because not only do we have multiple players, we have multiple difficulty settings that you can choose for in number. And we need to also do world building through unique behaviors. And this is one point that, like I said in the beginning, this is the second time I'm giving this talk. We didn't achieve this part. So what components do we need to form like an AI tool set? And this is, in order of the dependencies, you can see this pyramid forming. So you need to create some kind of pacing mechanism, and that depends on coordination, and that in turn depends on decision making, and that involves sensing, execution, positioning, and locomotion, and things like that. And this talk's supposed to be short, so I'm going to focus on two things that I think are pretty flashy and pretty nice, and that's the game pacing, so how we handle spawning enemies, how many enemies we spawn, where do we spawn them, and how they position themselves around you. And keep in mind that our game has a very heavy melee element to it, so they need to come up close, to engage the player. So the enemies, I'm going to call these guys agents in AI terms. This is the junior cleaner. He's basically a cannon fodder. He just melee attacks you and has not a lot of life. This guy is the senior, his older brother. He does a lot of damage, but is much more slower and has a lot more health. And obviously, he has priority over this guy. This is the classic archetypical suicider that when his life is low, he explodes and does splash damage. And this guy is the foreman, which is more of a ranged enemy type that drops boulders on your head and tries to run away from you and attack you in that sort of fashion. So, positioning. The question is, where do I need to be? Let's take this image as an example. We have 3 players, the green elements, and we have the red enemies around. So the question is, where do every one of these guys need to be, and who do they engage in particular, because they have 3 targets on screen. So problem definition, find best location in the world for what the agent is supposed to be doing, mind the other enemies around, keep up with the chaos, because you saw the player can just boost around and run around, and also show some kind of personality, because that's the flavor. This is the solution we came up with. It's a 3-step solution. Let's say the fridge is the player, and what we're going to do is find some position candidates. We're going to score each candidate, and then based on those scores, we're going to choose a point that is suitable for each agent. So, step 1, sample generation. And this means the points around the fridge. Basically, what we do is we create a set of candidate points in a radial pattern. And this is kind of abstracted behind this point provider interface. This was intended to be used in a more general fashion, so not just for players, you can have the level generate points as well. But in its current form, in its shipped form, we didn't do that. So that's another thing that we didn't expand upon. And some providers are shared, others are not. Like I said, the level stuff. And here's a video of how this works. So you see all those points generated around the players. Those are kind of parented to the player and follow him around. This is a much more granular generation that we have in game. This is just for debugging purposes and just to show it off how it works. In practice, we have around 6 rings, and in total about 60 points. Okay, then we're going to filter some points out. In this case, the points that are not reachable on the nav mesh, or they don't have line of sight on the nav mesh. See, for example, there's no need for an enemy to, it's not a valid position to put yourself behind the wall because you couldn't detect a player in that scenario. Okay, so this is sample generation. We're going to move on to step 2, sample scoring. This is done per agent. So each agent has its own stack of scoring stages. So you can think of each scoring stage as a scoring function plus some kind of modulation to modify it. And I'm going to give you some examples for that. And filters is an early way to bail out when evaluating a point. So for example, you don't want points that are not in view. So you just filter those out, and they count as score 0. How do we aggregate score? What we do is, for each stage, we evaluate all points. After we do that, we modulate and normalize those scores. And we get values between 0 and 1, and then the final score is the sum of all the scores of all the stages. And I'm gonna and one more thing, you see in this equation here, we have this world state that we need to pass in, and that's basically some kind of payload that contains information that is needed for those scoring functions to work. So you might have a scoring function that calculates distance to like all other enemies, and to be able to do that, you need some kind of data structure that contains all the positions for all the enemies and player positions and whatever kind of read-only information you think is relevant to those scoring functions. So I'm going to give you some examples. Sorry about that. Okay, so what kind of scoring functions we can think of? These need to be simple because they're basically building blocks, and if they're simple, you can aggregate them and create these stacks that are parametric, and you can have individual agent personality from that parameters. And examples of these type of functions could be, a dot or an average distance to other agents, or distance, or things like that. And modulation is, for example, how important is distance to the player versus, I don't know, the flanking angle. That's basically the weight. And you can play around with the normalization values as well. You can have like power functions that affect the result from the stages. And I'm going to show you. It's a lot easier if you see it in practice. This is a distance scoring function. You can see that this scoring function prefers a certain range around the player that's very close. And it being parametric, you can basically change, you can change the preferred range at runtime, or you can adjust the fall off. So you can see it here, for example. You see how fast that preference decays. And okay, this is a dot product. You see that white ball over there. You can pretend that's an enemy, and he will always prefer points between himself and the player. And again, if it's parametric, you can play around with the angle. You can see it decay slower or faster depending on the flank angles. Let's see that. Yeah. And these are very simple functions. It's just a one math thing. That's it. Right. So what happens if we merge those two together using the process I described? Here I've added an enemy agent to it, and this is the filter for the nav mesh. There's the distance and there's the dot product, and there we go. It's working already. All right. Come on, next slide. Okay, and this is a bonus thing. You can have a scoring stage that is basically the distance to the nav mesh edges. So you can get a kind of behavior where enemies try to avoid getting cornered, and this is how that looks. If the video would start. Steffi, can you help me with the video? Okay. See, and the points that are close to walls are have very low scores. Okay. Let's move on. Come on. And yeah, it's parametric as well. This clicker doesn't work right. Okay, so what about multiple agents? Can I have the video? You see, I add more agents, and this is a different problem because you want other agents to avoid the other's assigned position. The red guy has a lower priority than the green guys, and you see that he's considered inferior, and he chooses last the destination. Okay, and you can see that there's an emergent order. Like if I spawn another enemy that has a higher priority, you see they just naturally move out of the way. Okay, and then you just have to choose the point. This is pretty simple because you just choose the highest scoring point. I'm gonna rush a bit through these. Okay, let's talk about pacing. You need to offer some challenge to the player. You have to handle multiple players. You have to mitigate the problem of balancing, like I said, promote some kind of replayability, and offer some kind of level design tools to your designers. We want to create some drama reliably. So if we want to have a zone that is very intense, you need to be able to do that. It also has to feel unpredictable, so it's not repetitive. There's a very good talk from the guys that made Left 4 Dead that talk about this. And basically it comes down to a problem of when, where, and what to spawn. What we did is we created this engagement score, and we tried to measure how engaged the players feel. And we're tracking 4 different stats. Those are how much threat is in play, I mean how much enemies are on screen, how fast the threat increased in a certain period of time, and how much damage players receive, and how much damage they deal out. And of course you need some level design tools, so level designers can create hotspots and more interesting engagements. And this is how it looks. So the white line over here is like enemy engagement, the red one is damage taken, and the green one is threat. You see the engagement score is slowly beginning to pick up. You see the damage taken is kind of slowly going up, and when you're not taking damage, it starts to decay linearly. The engagement score is not linear, and it decays slowly like that. So what happens is, in most cases, when the engagement score drops below a certain threshold, we just spawn more enemies. Level designers have full control of what that threshold is, and they have master switches as well if they want to turn it off or on. We found out that you can't have a fully automated solution for this, and even though you have this system, you need your level designers to tailor specific settings for the levels, so it feels more natural, not just automatic. All right, and debug tools, very important. I encourage you to build and make use of debug visualizations and drawing and things like that. And they're very important to identify when things go bad and why did they go bad, and having tools like that, you can debug much faster. You don't need a coder to add breakpoints in code. The math behind this is pretty straightforward. Different stats that we track are interpreted differently. For example, like I showed, the damage taken decays linearly and grows linearly. As you receive damage, it just adds. It's not so simple for the other ones. The final score is basically an exponential moving average over a time series, and thus you can prefer the closest values are more important than the tail in the buffer. So when the engagement drops to a certain threshold, then you spawn more enemies. And yeah, like I said, level control, very important. So this is the first step. Where to spawn? We have the level divided in zones with connectivity info. So you have you can know where you can go from each zone. And we have defined these what we call spawn locations that spawn locations that provide points that are spawn position candidates. The points are generated when the level starts. It's procedural, and it uses Poisson distribution to sample the level. The level designers place these bounded volumes in the level, and the points get generated at level start. Point information is updated every frame, such as if there are zones that are blocked off, so inaccessible, they are marked accordingly, and those are discarded when considering. Okay, so basically like this. This is a top-down view, and a zone is a very loosely defined thing. It's basically what we consider an important position in a level. So this is how it looks like. I don't know if you can see it, but the level is, this is a debug visualization. The level goes like that in an L shape. The player is in the bottom left of the screen, and this is what all points look like in the beginning of the level. We have this concept of ambiental enemies. So when you move through the level, you want to have a number of enemies that are spawned just idly moving around. And what we do is we take a percentage of these points and we consider them as ambiental spawning points. And you see that the player has those 3 circles around him, 3 ranges. What this means is that when one of those ambiental points goes into the red circle, we spawn an idling enemy. If that enemy doesn't get killed or engaged and moves out of the blue circle, we unspawn him and put him back in the point. The points that are in the black circle are considered in view and marked as such, and the ones in the red circle are out of view. And we use them like this. We have enemy events that in their simplest form is basically a timeline where you can say, for example, in this case, it says, at time 0, spawn an enemy charger. This can be scaled, so if you have 3 players, it spawns 2. If it has 4 players, it spawns 3. And you can say it has a setting that you specify that don't spawn these guys in view. So it uses the points outside of view, the ones in the red circle. And then you have another spawning event at t+2 that spawns a number of junior cleaners, and this time in view, and we have this concept of spawn proxies. And what this means in reality is you have that drop pod effect. So it intentionally spawns enemies in view using that drop pod effect. And that's about it. Any questions?
Hi, so unfortunately we don't have time for live questions because
you can catch me after this.
Please catch Radu after. And let's have on stage Daniel from the Hip Meta game.